Reinforced concrete beams, stirrups example 2. So in this example, we do have a two simple supported beam with a concentrated live load of 50,000 pound force and also a distributed dead load of 12 pound per feet. The length of beam is 10 feet and the cross section is provided like with one a tensile rebars at the distance of 4 inch from the below of the section. Width of the section is 14 inches and the height is 22. So effective depth is 22 minus 4, which is 18 inches. Let's approach the problem. So in this example, we have a cross section which F prime C provided to be 2500 pound inch squared and yield stress of steel is 50,000 pound inch squared. If we do know area of tensile steel is a 3.8 inside the cross section inch squared, based on a little bit more capacity calculation, capacity calculate minimum amount of shear reinforcement, which is the shearing stirrups. If we do know the center to center stirrups spacing, if we need them, the spacing of the stirrups are 12 inches apart. So first of all, in this problem, we do need to go through the diagram of the shear, calculate the shear inside the beam, because stirrups are related to shear. So if you consider the distributed dead load of W, which is 12 pound per feet, and if you draw the shear diagram, it just goes up by the half of that amount. So 12 times 12 distributed load times the length of the beam over Q is the share of this support, then linearly change, goes down, and then come back to zero at support B. So the share of distributed for dead share of shear for distributed dead load is 60 pounds force, and for concentrated live load of P, which is 50,000, so it just is uniformly distributed between the support. So this is 25,000 and the other one RA is equal to RB, and each of them is 25,000. Then VU ultimate shear is a coefficient times dead load plus another coefficient times live load, and definitely load here is shear. Place of ACI code, we can calculate what VC is. V of concrete is 2 times B, 2 times width of our block times effective depth times the square root of F prime C, which is provided in problem statement. We do know ultimate shear is a 1.2 times VD plus 1.6 times VL, which is a live shear plus a dead shear. And also the reduction factor for shear is 75%. And we do also know this term, if VU is greater than a half of V times VC, V is 75%, then the stirrups are required. And if not, we do not need any stirrups. So let's calculate the very first one. So VC here is 2 times B, which is 14, times 18, which is a height, minus T minus 4, and that's a 22 minus 4, which is 18, and that's effective depth, times a square root of 2500, which is F prime C. And it just gives us 2500 to 25,200 pounds. And if you do the mass for VU, it just gives us a numeric value of 40,072 pounds. And definitely VU is greater than a half of a smaller coefficient than 1 times 25,000. So we do need the stirrups. So let's go back to again our VC. A share of concrete from shear is 25,200 pounds, and ultimate shear is 40,072 pounds. So again, if VU is greater than half of V times VC stirrup required, go back to ACI code for required minimum and permitted stirrups. If VU is smaller than that, no stirrups. If it's bigger than that, we do need to use stirrups based off formula. And let's see how that goes. So at the same time, if we do need stirrups, and at the same time we do know based off ACI code, if we do know that's ACI, American Concrete Institute, that's ACI 318 version 2019. It just says if you do need to have stirrups, and if VU, so if you need a stirrups, it means already VU is definitely greater than half of V times VC. Now this time it says if you need stirrups and it's still bigger than V times VC itself, then use this formula. Let's check all VU, which is definitely greater than, because our VC is 25,000 and V is 40, so definitely VU is greater than a coefficient smaller than 1 VC. So we definitely need to use the ACI code 22.5.8.1, and if you rearrange that, it just gives us if you use that, it just gives us a VS of 28, almost 28,000 pound forces. So, and this part of the code, it just says VS. VS is equal to this equation, which is when you do know what the area of our stirrups is, you can calculate the shear and also the distance between them. If you do know, for example, you can play around with this equation. If you do know what the S is, you can use the other to calculate or find out what S is, what is the distance between stirrups. In our case, it just provided in the problem statement. If we do know the distance, if we do need to have stirrups, the distance of the center to center is 12 inches apart from each other. So from previous part, we just calculated Vs from the previous equation, and we do to replace the equation to get what is the area of the stirrups. So if you do that, it just gives us the Vs, which we just calculated in previous stage, which is almost 28,000, times the distances of stirrups, which is provided 12-inch in problem statement, over Fy, which is yield stress of steel, which is 50,000, times effective depth of our cross section, which is 18 inches. And if you do so, it just gives us a numeric value based off inch squared. So AV, area of stirrups, is 0.038 inches squared. Thank you. Solve more problems.